Welcome to our lecture online. In this video, we're going to show you what is coming up in this particular series. We're going to be talking about electrical engineering. There's a lot of topics to be covered. These are basically the 19 chapters that we're going to cover, starting with some basic concepts, then the basic laws of circuits, some circuit analysis, the basic concept of circuit analysis, then we'll get into some specific circuit theorems. We'll talk about capacitors and inductors in circuits, operational amplifiers, also known as op-amps. We'll talk about circuits that can be solved using first-order techniques or first-order differential equation techniques, and circuits that will require second-order differential equation techniques to be solved. We'll talk about AC circuits and phasors, so we'll talk about phasor diagrams and the difference in phase between the current and the voltage. We'll talk about sinusoidal steady-state analysis, so we'll do circuits with steady-state conditions in the circuit. Then we'll talk about AC power analysis. We'll then talk about the three-phase circuits, magnetic coupling, frequency response, and then finally we'll get into the more difficult concepts such as Laplace transforms, applications of Laplace transforms, Fourier series, Fourier transforms, and finally two-port networks. So a lot of material that's coming up. I've had some requests to do Laplace transforms, Fourier series, Fourier transforms, and so forth. I figured this is a good place to put them in a course of electrical engineering. Hopefully you'll enjoy these. Stay tuned and we'll get started on number one. Welcome to Lecture Online. In this video we're going to take a look at some basic symbols that you might encounter when we look at circuits in this course. The symbols represent real devices. Of course, the symbols are not really true picture representation of those, but when you get used to symbols, it becomes as if you're looking at the real thing. Here we have a resistor. A resistor is simply a squiggly line going back and forth like that. The resistor, the symbol that we use for resistance is R, and the units we have for resistance is ohms. We use the symbol, the Greek letter omega, to indicate ohms. That's the unit of resistance. When you have two lines together like this inside a circuit, this is called a capacitor. That represents two capacitor plates very close to one another, opposite to one another like that. This is called the capacitance, and the units we use is farads, and the letter for that would be F. Inductors or coils are drawn like little springs like that on the side. L stands for inductance, and the units we have for inductors is henries. We use the letter H for henries. Sometimes we have what we call the load resistor. We have an entire circuit and we attach another device onto that circuit. That device usually has some sort of resistance, and we call that the load resistor. It's not really part of the circuit. It's simply we load the circuit with this device or with this resistor. So it's called the load resistor, and we have a sub L to indicate that that's the load resistor. Just like a resistor, the units are ohms. We use the Greek letter omega. Sometimes we have what we call variable resistors. Resistors that we can vary, so we can vary the resistance of the resistor. We draw a little arrow through that that indicates that the resistor can be changed in value. We also need to have power sources or voltage sources. In this case, we have what we've drawn here, a battery. A battery is a series of lines, long and short lines. Where the long side starts, that's where the positive side of the battery is. Where the battery ends with the short line, that's where the negative end of the battery is. Sometimes we also call the battery the EMF, the electromotive force, because it basically forces current through the circuit. We use the letter V to indicate volts for the battery, and that's also then the units. The units and the symbol for the battery is actually the same. We use volts. We can also have variable capacitors. In some circuits, we can vary the capacitor. Therefore, we have a capacitor symbol with a little arrow through it. Some other things that we need to know is sometimes we have not just a steady state or direct current voltage source. Sometimes we have an alternating current voltage source. An alternating current voltage source produces an alternating voltage. It increases, decreases, goes negative. Actually, the voltage becomes positive, negative throughout its cycle. So it produces what we call AC voltage, and we have this sine wave symbol inside a circle to indicate that. We also will be dealing with certain solid-state devices. A transistor is one of the simplest form of solid-state devices. We have a current coming in, another controlling current that determines how much current will come out of the device. We'll learn more about transistors. Another solid-state device is a diode, which basically only lets current through in one direction, not so much in the other direction, maybe just a small amount of lead current. So a diode indicates what direction it will allow the current to flow. And finally, we have something what we call connection to ground. This is a ground connection. We have a series of small lines that get shorter and shorter and shorter. That means when your circuit is connected to ground, the voltage will be zero at that location, and that then becomes your reference voltage of the circuit. Those are just some basic circuit symbols that we'll be using throughout. And so to be familiar with these is very useful, very beneficial to become familiar with these symbols. There's many more symbols, of course, but if you know these, you have a good repertoire of things that you can draw on when you start building and looking at simple circuits. And that's where we start. Welcome to Electron Line. One of the most confusing aspects of electrical engineering versus basic science and physics when we talk about current is what is the direction of the current? Well, the conventional direction of the current is that current flows from a power source and from the positive end of the power source to the negative end of the power source. That's the conventional current. That's basically the current concept set up by Benjamin Franklin. He claimed that there's positive charges flowing through the circuit. However, at the time, we didn't understand what the positive and negative charges were. We knew there were positive charges. We knew there were negative charges. We didn't know which ones were flowing through the circuit. So the assumption was made, let's just call it the positive charges moving through the circuit. We call that the IEEE convention. It is the conventional direction of the current from positive to negative. However, we all now realize that it's the negative charge that are actually doing the moving. It's the negative electrons in the atoms of material that are moving through the circuit. In essence, the current, the real charges are moving in the opposite direction from the negative end of the battery to the positive end of the battery through the load resistor. What we're going to do from now on is we're going to assume that the positive current, the conventional current, is flowing indeed from the positive to negative side, while we understand that the electrons are flowing in the opposite direction and the electrons then form the negative current. So that way we're always safe. We can say the conventional current runs from or flows from positive to negative, and the electron current flows from negative to positive, and we call that therefore the negative current. The definition of the current is defined here by this differential equation that I is equal to the change in the charge per unit time. We really don't mean the change, we mean the amount of charges flowing past a particular point. So if we take any point on the circuit and we watch current going by that point, we can say that the current flow is equal to the amount of charge that passes that point per unit time. The charge is usually indicated in terms of coulombs and the time in seconds. So coulombs per second then gives us amps or amperes. We use the symbol A to indicate the amount of current that we have. 1 amp is determined or defined by the ratio of 1 coulomb per second. When you know we have a current flow of 1 amp, you know that there's 1 coulomb of charges passing that point every single second. A coulomb of charge is equal to 6.24 times 10 to the 18th unit charges. The unit charge, of course, the charge we have on a single electron or a single proton. Now here again is where people get confused. They say, well, if the charge is positive and yet you indicate negative charges, electron charges, how can you justify that? An electron charge is simply a unitary charge, the simplest charge in the universe. Therefore, we call an electron charge a single charge, and a coulomb has 6.24 times 10 to the 18th of those. Again, we think of coulombs as positive, we think of current as positive charges flowing. Finally, if you want to then calculate how much charge has gone past a certain point in the circuit, the charge that is past that point is equal to the integral of the current at that point times dt integrated from 0 to t. So how much current has flown over a certain amount of time, especially if I is not a constant but a variable, then of course we want to keep track of that, and the total charge will then simply be the integral of the current times dt. That's the basic concept of current. From now on we realize current is positive charge flowing from the positive end of the battery to the negative end of the battery. If we all keep that in mind, then it'll be a lot easier to follow the videos that are to come. And that's how we look at current. Welcome to Electron Line. Now we're going to take a look at the current, and in particular, the comparison between direct current and alternating current. When you hear the term direct current, it usually refers to a battery source which can only push current in a singular direction from the positive end towards the negative end around the circuit, and so current always flows in a single direction in that particular path, from positive to negative. So when we then graph the current as a function of time, you can see it's a steady state current, always the exact same amount of current. The way we can calculate that current is by using Ohm's law that says that the current is equal to the voltage in the circuit divided by the resistance of the circuit. In this particular case, if we have 10-volt battery source and a 2-ohm resistor in the circuit, then the current will be 10 volts divided by 2 ohms, which is 5 amps, and so that will be a steady state or direct current of 5 amps. Now, what if the voltage source is an alternating voltage source? It puts out a voltage according to this equation, V max times the sine of omega t. Omega is the frequency of the oscillation of the circuit. And of course, when you want to then write it like this, omega is equal to 2 pi f, where f is actually the frequency of the changes in the voltage. Omega is then the radial frequency according to that. Now notice that when you have an alternating voltage source, basically what you're doing is, at some moments in time, you're pushing electrons in one direction. At other points in time, you're pushing electrons in the other direction. Of course, since current is opposite the electron flow, it still doesn't matter. You still have current flowing in one direction and then in the other direction as time goes on. Therefore, when you draw current as a function of time, you end up with this type of graph. It looks just like a sine wave. Sometimes the current is zero at that particular moment in time. It reaches a maximum current in one direction, goes back to zero. Now the current changes direction, starts flowing in the opposite direction, reaches a maximum value in the opposite direction. Then again, it begins to slow down, comes back to zero, reverses direction, and then again it builds up to maximum value and so forth. And it continues on like that. We call that alternating current or AC current. The equation will be the current as a function of time will be the maximum current you can reach times the sine of omega t. Again, omega is 2 pi times the frequency of the oscillation of the voltage source. Now, then you can say perhaps that the average current would be zero because half the time it's flowing in one direction, the other half of the time it's flowing in the other direction. But that's not really true. Well, in a sense, the average current is zero, but the effective current is what you get when you take the maximum current and multiply it by the square root of 2 over 2. That's called the root mean square value of the current, and we'll get into that in more detail later. But what that means is that the effective current is that it's 0.707 times I max. In other words, if you want to replace it by a DC equivalent current, it would be 0.707 times I max of the alternating current. So alternating current, even though it's flowing in opposite direction, gives you the impression, at least the components in the circuit feel as if current is being pushed into one direction only, and the effective value of the current would be 0.707 times I max. Now at least you have some feel for the difference in current. We'll still have to talk a little bit more about the fact that you still have a positive and a negative side. Current still is pushed to the circuit because there's a potential difference, and we'll have to square that away with the concept of alternating voltage and alternating current. But at least at this point, just recognize the difference between direct current and alternating current, and that whenever we talk about alternating current, we have to talk about the effective current in the circuit. That's a good start. Let's stay tuned and see what else we have in our next coming videos. Welcome to our lecture online. In this video, we're going to talk about voltage. What does voltage mean? Well, the basic concept comes from this. Let's say we have a capacitor plate set. On one side, we have a positively charged capacitor plate. On the other side, we have a negatively charged capacitor plate. And let's say that they're apart a distance d from one another. We then realize there's an electric field that exists between the positive and negative charges. The electric field will be directed from the positive charge to the negative charge. If we now place a small charge, a positive charge, on the right side of this capacitor, we then realize that it's being attracted towards the negative charge here and being repelled by the positive charge there. So if we want to move that charge from the right side to the left side, then it's going to require a certain amount of work, a certain amount of force to get it there. The amount of force required is equal to the size of that charge in coulombs times the strength of the electric field. The stronger the field, the greater the disparity of charges, the more force you're going to need to push that charge across. The work is defined by the force required times the distance. So if we push that charge all the way over to the other side through a distance d, the amount of work we've done is equal to the force times d, and the force that that charge experiences is the size of the charge times the strength of the electric field. So it's Q times E times d. That's the work done. Now, the definition of voltage. Voltage is defined as the amount of work done to move a charge across this distance here where there's an electric field, the amount of work done to do that, divided by the size of the charge. And that makes sense because let's say that the charge was twice as big. Let's say we have 2Q there. So let's say we have twice the charge. It would then require twice the force, twice the charge, therefore twice the work, and we will have twice the charge, and you see that that ratio will always be the same regardless as to the size of the charge that we use. So it's always the ratio of the amount of work done divided by the charge used, and regardless how big we make that charge, that ratio is always the same, and that is then defined as the voltage. It's the work done to get a charge across from the left side to the right, or from the right side to the left side in this case, from the negative charge to the positive charge, through an electric field, divided by the charge required. If we plug in, if we get rid of these 2's again, right here, if we plug in what work is equal to, we can see that the work is equal to Q E times D divided by the charge Q. The Q's cancel out, which means that the voltage then is defined as the strength of the electric field times the distance between the left side and the right side of that field. The voltage can be thought of in two ways. It's equal to the amount of work we need to do to get a charge moved through an electric field divided by the size of the charge, or simply the potential difference or voltage is equal to the strength of the electric field times the distance. Now a volt is defined therefore as a joule per coulomb. Remember, it's work over charge. Work is in joules, charge is in coulombs, so a volt is defined as a joule per coulomb. In other words, if we have a 1 coulomb of charge, and it takes 1 joule of work to get it across, that means that the voltage between those two plates is equal to 1 volt. That's how we want to look at it. If we have a battery, and we have a positive end of the battery, and we have a negative end of the battery, and the volts across the battery is 10 volts, we can say that the voltage at A is 10 volts higher than the voltage at B. So sometimes we talk about potential difference or voltage difference. It is how much more volts we have on one side compared to the other side. In this case, A is 10 volts higher than B. B could be 100 volts, then A would be at 110 volts. Whenever we talk about the voltage of a battery, we really talk about the difference in the voltage or the potential difference. In this case, when we talk about volts from A to B, that is equal to volts at A minus volt at B. Since A is bigger than B, it'll be 10 volts minus 0 volts, which is a 10 volt difference. But if we talk about VBA, this is equal to V at B minus V at A, which is equal to 0 volts minus 10 volts, is equal to minus 10 volts. When we go from B to A, we increase in voltage by 10 volts. If we go from A to B, we decrease by 10 volts. That's a negative voltage direction. Another way of looking at voltage, V, voltage, is equal to the potential difference. Potential difference means the voltage difference between 2 points on the circuit. Sometimes it's also called the EMF or the electromotive force. And one of the reasons why we think about it as the electromotive force is because voltage is really the amount of volts you have on a circuit or in a battery determines how much push charges feel to move through the circuit. Another way of looking at voltage is to say that the voltage represents the force or push charges feel. Of course, charges don't really feel anything, but if you think about it, if you're a charge and there's a voltage difference there, you're going to feel a push through the circuit. It's going to feel as if you're being pushed through that circuit by the voltage difference. The bigger the voltage difference, the bigger the voltage across that battery, the more push that charge is going to feel. The greater the voltage, the greater the force or the push that the charges feel inside the circuit. The bigger the potential difference, the greater the force, the more push to get the charges around the circuit. And that's why very large voltages can be very dangerous, because large pushes can actually become dangerous when you get near that. Charges may get pushed through your body if you touch a circuit and if the potential difference of the voltage is very large. Again, voltage, think of it as that thing that pushes charge through circuits. The bigger the voltage, the bigger the push, and that's a good place to start. Welcome to Lecture Online. In this video, we're going to talk about power. What does power mean? Well, power, by definition, is work over time. How much work you can perform per unit time. Now, it turns out that pushing charges through a circuit, that takes work. And the more charges you push through a circuit, the more power it requires. Or the faster you push charges through the circuit, the more power it requires. The battery, or any sort of power source, will provide that power. And the equation that we use to indicate how much power the battery produces is equal to the current that the battery pushes through the circuit times the voltage that the battery has. If this is a 10-volt battery and it produces 10 amps of current, then the power provided will be 10 volts times 10 amps or 100 watts. The units for power is watts, just like you see when we do regular work or like the power of an engine or so forth. Now, there are other components in the circuit that the current is driven through, and the more resistance you have in a circuit, the harder it is to push the charges through, and the resistor therefore consumes that power. The equation that we use to indicate how much power a resistor consumes, it is the current squared times R. So let's put some numbers in so you can see what that looks like. Let's say we have a 10-volt battery. This is 10 volts. And let's say we produce 10 amps of current. This is 10 amps. And let's say that our resistor is equal to 50 ohms. Let me write it over here. Our resistor is equal to 50 ohms. How much power is provided by the battery? In this case, the power provided by the battery is equal to 10 amps times 10 volts, which is equal to 100 watts. Here we can say that the power is equal to the current squared, that would be 10 amps squared, times the, let's see here. I need to be careful. I need to make sure that I use the right amount of resistance, because we also know that I is equal to V over R. So if there's only a 10-volt battery, it's not going to produce a 10 amp current. What I need to do here is change this to the appropriate resistance of 1 ohms to make everything work out right. In this case, I is V, 10 volts, divided by R, which is 1 ohm, which is 10 amps. Everything works better now. Again, going back to the power consumption equation for the resistor, power equals current squared times the resistance. The current was 10 amps. We square that. The resistance is 1 ohm. You can see here that power is equal to 10 squared. That's 100 times 1, or that would be 100 watts. Notice in this case that the power consumed by the battery is equal to the power provided by the power consumed by the resistor is equal to the power provided by the battery. In many cases, like whenever we single out the source that provides all the power, we single out the component that consumes all the power, those should of course then be equal to one another. But there's plenty of cases where we have a source that provides power and multiple components that consume power, and so any one of those components will only consume a fraction of the power provided by the battery or by the power source. One more thing we should mention. Notice that we could have a current flowing in the direction indicated by the battery. Sometimes we have the current flowing in the opposite direction, because there may be another battery or another power source that is larger than this one, causing the current to flow in the opposite direction. If the polarity of the battery, the positive end and the negative end, are such that it's indicating the same direction as the direction of the current, then the power provided by this battery will be positive. A positive 5 amps times 4 volts is 20 watts in this case. But if something else is drawing current in the opposite direction, then this battery does not provide positive power. Then we have negative power across the battery because the current is being driven in the opposite or negative direction. So we want to make sure we keep that straight as well. Again, the difference: batteries produce power, resistors or sources or loads on the circuit, they consume power. The equation we typically use for providing power is current times velocity. The equation we typically use for consumption of power is I squared R. In many cases, you'll get the very same result by calculating both the power provided and the power consumed, unless there's other devices that are also consuming power and you're not considering those. That's what we mean by power in a circuit. Welcome to Electron Line. In this video, we're going to talk about different kinds of circuit elements, and in particular, the passive and active circuit elements. So what is the difference between passive and active circuit elements? The passive circuit elements are things such as resistors, capacitors, inductors. They do not produce any current, they do not produce any voltage, they are not capable of producing any energy or inputting energy into the system or into the circuit. In opposition to that, we have active elements such as generators, batteries, and operational amplifiers. They are capable of putting energy into the system or into the circuit. Generators can produce a voltage or a current, so can batteries, so can operational amplifiers. When we have a voltage source or a current source that is independent of anything else, we call them independent sources or voltage sources or current sources. If we have sources that are dependent upon other sources to put in a certain amount of current or to apply a certain amount of voltage, we call them dependent sources. All of them, of course, are active sources. Ideal independent sources can produce an ideal voltage or an ideal current independent of anything else in the circuit. They can produce or they can provide as much current as the circuit can possibly draw, independent of how much current the circuit will draw. No matter how much it draws, they can produce all of it and yet provide the potential difference across the circuit. It will not drop. Some sources, when you start drawing too much current, the voltage across the terminals begins to draw down or begins to decrease, and so therefore it's not a consistent or a totally independent source. So there are some differences there. An ideal dependent source can still produce sufficient amount of current or sufficient amount of voltage, but it depends on that through some other source. It must get that energy, or it must be controlled through some other active element producing that energy so they can maintain the current or maintain the potential difference. There's 4 different kinds of those. We call them either the VCVS, the CCVS, the VCCS, or the CCCS. What that stands for, V stands for voltage and C stands for current. V stands for voltage and C stands for controlled. So we have voltage controlled voltage source, we have current controlled voltage source, we have voltage controlled current source, and we have current controlled current source. So that's how we read those 4 acronyms. In other words, we can have a voltage source that can either be controlled by some other current or some other voltage, or we can have a current source that can be controlled by some other voltage or some other current. The symbolism is important here. If it's a completely independent source, then we draw a little circle around it. A battery can be assumed to be somewhat of an independent source, and so therefore it can produce potentially all of the current and provide all the voltage required for the circuit. Although batteries are subject to a drawdown in current. In other words, if the circuit demands too much current, the battery may not be able to fulfill that demand. But it's approximated to do so. But we can have voltage sources or current sources that are independent and provide all the current and voltage required by the circuit. If so, we draw little circles around them. Now when we have a plus or minus, that means the same thing as if we had a little squiggly line like a little sine wave. This means time dependent or time varying. When we have a time varying source, we can either put a plus minus in there, meaning that it changes direction. It's an AC current. Sometimes it's positive, sometimes it's negative. It switches around, just like a sine wave like that. If we have an arrow like this, that means that it's a current supplier. It will produce all the current the circuit will require, and it will do so independently of any source. So whatever current the circuit requires, it will provide so. If we draw a little diamond around it like that, this can still be a time varying source. Same like here, it can still be a current source, but if we draw a little diamond around it, then it's a dependent source, meaning the voltage supplied or the current supplied depends upon some other source. This is controlled by another source, so therefore this produces a voltage, a time varying voltage, or a current, could be a time varying current, due to the presence of another source or due to the control of another source. Those are the different kinds of active elements to be separated from what we call passive elements. Remember, these don't produce any energy. Again, an active element is something capable of providing a voltage or a current, which means it can put energy into the circuit. Hopefully that clears things up. And so when you see these acronyms or when you see these kind of symbols, now you know what they mean and now you know how to deal with them. That's how we do it in electrical engineering.